the past few slides, we introduced different types of recommendation systems and also explored some of the basic elements of reinforcement learning. We found that reinforcement learning problems evaluates different actions when the agent is in specific states. Now the action taken generates a certain reward, or in other words, we get a feedback on how good the action was based on the reward we got. However, we won't get a feedback as to whether the action taken was the best available. And this is what contrasts reinforcement learning from supervised learning. So in a typical supervised learning setup, the feedback is instructive and gives you the quantum of correctness of an action based on the errors. Now, since the reinforcement learning is evaluative, it depends a lot on exploring different actions under different states to find the best one. Now, this is called the exploration versus exploitation trade-off, which we discussed in the previous post. Now, this trade-off between exploration and exploitation is the bedrock of reinforcement learning problems, like the K-armed bandit. Now, let's dive in a little bit more. So one major dilemma in problems like the bandit is a choice between exploration and exploitation. We talked about in the previous slide. Let's explain this with our context. Let's say after few pulls of the first 4 levers, we found that the lever 3 has been consistently giving good rewards. So in this scenario, a prudent strategy would be to keep on pulling the third lever as we are sure that this is the best known lever. This is called exploitation. Now in this case, we are exploiting our knowledge about the lever which gives the best reward. We also call the exploitation of the best known lever as the greedy method. However, the question is, will exploitation of a current knowledge guarantee that we get the best value in the long run? Well, the answer is no. This is because so far we have only tried the first 4 levers. We haven't tried other levers from say 5 to 10. Now, what if there was another lever which is capable of giving higher reward? How will we identify these unknown high valued levers if we keep sticking to a best known lever? And this dilemma is called the exploration versus exploitations. So having said that, resorting to always exploring will also be not judicious. It is found that a mix of exploitation and exploration yields the best value over long trend. So methods which adopt a mix of exploitation and exploration are called psi-greedy methods. So in such methods, we exploit the greedy method most of the time. However, at some instances, say with a small probability of say psi, we randomly sample from other levers also, so that we get a mix of exploitation and exploration. So we'll explore different psi-greedy methods in the subsequent sessions. So in our discussion so far, we have seen the dynamics of reinforcement learning involves actions taken from different states, which yields rewards based on the state action pair chosen. Now, the ultimate aim is to maximize the rewards in the long run. So in order to maximize the overall rewards, it is required to exploit the actions which gets you the maximum rewards in the long run. However, to identify the actions with the highest potential, we also need to estimate the value of that action over time. So let's first explore one of this method called simple averaging method, which will give the value of that action over time. So let's denote an action A at time t as QTA. So that's the action A at the value of the action A at time t. Now using a simple averaging method, we can estimate the value of that action by summing up all the rewards received for that action divided by the number of times that action was selected. Now this can be represented mathematically as shown here. So here the R1, R2, etc. are the rewards which we get every time that action is selected. Now by adding up all those rewards and dividing by the number of times that particular action was selected, you get a estimate of the value of that action. Now how we know that estimate of value is a moving average, so which means that there would be further instances when action A will be selected and corresponding rewards received. However, it would be very tedious now to sum up all these rewards and then divide by the total number of instances, like the earlier formula. So to avoid such tedious steps, the above equation can be rewritten as follows. So here this is a simple update formula where Qn plus 1 is the new estimate for the n plus 1th occurrence of action A. Now Qn is the estimate till the nth try. Now Rn is the reward received for the nth try, and Qn is the total estimate of the reward which was received till the nth try. So in simple terms, this formula can be written as new estimate is old estimate plus step size into reward minus the old estimate. Now here, for a simple averaging method, the step size, which is a hyperparameter here, is the number of times that particular action was selected, the reciprocal of the number of times that particular action was selected, or 1 by n in short. Now let's see the complete algorithm which we are going to implement in code later on in the subsequent post, because now we're going to code these simple averaging method for the bandit problems to get a deeper understanding in Python, and let's walk through the complete process which we are going to take. So before we start coding in Python, let's walk through the complete process. Now the first step is to initialize the values for the bandit arms from 1 to k. Now let's say for example there are 10 arms, so k would be 10. So usually we initialize a value of 0 for all the bandit arms. Now when we start off with, we initialize a value of 0. Now then we also define matrices to store the value estimates for all the arms, like the QTA which we discussed about earlier, which is the value of a specific action over a period of time, and this also we initialize it as a 0. So we also define a matrix to store the tracker for all the arms, in other words, that how many times each of those arms were pulled over time. So that also we track. Now we start an iterative loop. The first process is to sample a random probability number, and if the probability number which we have randomly selected is greater than psi, so first we initialize a value of psi also, usually say 0.1 or 0.05 or whatever, and then so if the probability value is greater than psi, we pick the arm with the largest value. Now we have already made an estimate of the arms in QTA, right? For each of those arms it will be QTA. Now when in the initial period it will be all 0, but over time there will be some estimate which will be accumulated for each of the arms. So if the probability value is greater than psi, we pick the arm with the largest value. Now if the probability value is less than psi, we just randomly pick one of those arms. Out of, if there are 10 arms, we randomly pick one of them. Now then we also generate a reward. Now reward is also generated through a Gaussian process, which we will see next, when we start coding. Now once we get the reward and we know which action was selected, we keep on updating the matrices which we earlier defined. One of the metrics is about updating the number of times a particular arm was pulled with 1. Every time an arm is pulled, you update that particular arm index by 1, and then we also update the reward or the value of that particular arm, using that from that old estimate, or the new estimate is the old estimate plus step size into reward minus old estimate, that formula which we saw. So this is the complete process which we will follow. Now let's get into coding these algorithm and then see how we can implement this bandit problem. Now to understand this is important, because we will be using one of these process when we ultimately build our recommendation system.